A modern bridge opened to celebration, and within hours it began to sway, not in a storm, not under catastrophe, but under footsteps. On opening day in June 2000, the Millennium Bridge moved laterally in ways its designers had not predicted. Pedestrians unconsciously synchronized their stride, oscillations amplified, the structure fed back into itself. Within days it was closed. A billion-dollar urban tunnel project meant to untangle traffic instead tangled mathematics. Beneath Boston, the Big Dig suffered alignment complications, leakage, settlement modeling errors, and cost overruns that spiraled past $10 billion. In Dubai, the Burj Khalifa required immense computational modeling to predict how wind shear and foundation settlement would behave at unprecedented height. Without simulation, it could not exist. These are not failures of intelligence. They are consequences of scale. Because when a structure grows, it does not merely become larger, it becomes different. Engineers understand this with quiet respect. A 1-meter model behaves obediently. A 200-meter reality does not. Thermal expansion compounds across distance. Materials creep. Steel flexes. Concrete shrinks. Soil compresses unevenly. Measurement instruments accumulate drift. Minor angular misalignments become massive spatial deviations over long spans. Error is rarely dramatic at first. It accumulates. Scaling introduces new classes of error, non-linear phenomena that simply do not exist at small size. A bridge deck that is perfectly stable at 10 meters may resonate unpredictably at 300. A building foundation that appears uniform at local scale may reveal heterogeneity across hectares. What was negligible becomes dominant. This is the central paradox of megastructures. Size magnifies imperfection. And yet, on a limestone plateau west of Cairo, there stands an object that appears to violate that rule. The Great Pyramid of Giza spans roughly 230 meters on each side. Its original height approached 146.6 meters. It consists of approximately 2.3 million blocks, and its geometry does not appear to degrade with scale. Measured carefully by surveyors beginning with Flinders Petrie in the 1880s and refined by modern engineers such as Glenn Dash and Mark Lehner, the data are quietly astonishing. The base is level to within a few centimeters across 13 acres. Its orientation to true north deviates by only about 3 to 4 arc minutes, roughly 1/15th of a degree. Its corner angles deviate from perfect right angles by approximately 45 arc seconds, less than 1/100th of a degree. Pause for a moment. 45 arc seconds, across a structure larger than many city blocks. Modern stadiums, airports, and skyscraper complexes often struggle to maintain such angular coherence, even with laser theodolites, GPS calibration, and digital modeling software. The pyramid achieved it with copper tools, stone hammers, sighting instruments, cords, and rods. This is not romanticism, it is measurement, and measurement is unforgiving. In engineering and physics, there is a concept known as scale invariance. A system is scale invariant when its structural or geometric relationships remain consistent as size changes. Fractals are scale invariant. Certain physical laws are scale invariant under transformation. Self-similar systems exhibit this property. Enlarge them, and the pattern persists. Most physical constructions are not scale invariant. When you enlarge them, stresses redistribute, material properties behave differently, error multiplies, control becomes more difficult, not less. Yet the Great Pyramid presents an uncomfortable observation. Its geometric discipline appears consistent from microscale to macroscale. At the micro level, surviving casing stones, including one preserved in Edinburgh, show joint tolerances averaging around 0.5 millimeter, not centimeters, millimeters. At the macro level, the base remains astonishingly square. The slope angle of roughly 51 degrees 51 minutes is preserved with remarkable consistency up the faces. What we do not see is geometric drift proportional to size. In most modern megaprojects, error grows with length. A deviation of a millimeter at 1 meter becomes a deviation of meters across hundreds. Correction systems are layered constantly to prevent cumulative distortion. But here, across 230 meters, the distortion remains constrained. This is the anomaly. Now one might suggest luck. But luck does not produce consistent angular deviation under 1 arc-minute at 4 separate corners. One might suggest lost technology, but no steel, no optics, no electronic instrumentation, no calculus. What remains is something more unsettling: discipline. Consider what scaling usually does to measurement systems. Cords stretch, wooden rods warp, temperature shifts alter length, survey markers shift subtly over time. The longer the baseline, the greater the potential for cumulative drift. And drift is the true enemy of scale. If your baseline shifts even slightly, every perpendicular derived from it inherits that shift. Every layer built atop it propagates distortion upward. Small misalignments become visible fractures. Modern engineers fight this constantly. They recalibrate, they compensate, they simulate. But what if the pyramid builders approached the problem differently? What if they did not rely on correction after error appeared, but instead engineered a baseline so stable that error had little opportunity to accumulate? Because here lies the key tension. If the base of the pyramid was established using a gravity-defined reference plane, perhaps water-filled trenches carved into bedrock, then the initial zero was not dependent on instrument precision. It was defined by Earth itself. Gravity does not drift, it does not expand with temperature, it does not stretch. If your baseline is anchored to gravity and your perpendiculars are derived from geometric constructions rather than numerical approximation, then scale becomes propagation, not amplification. That difference is subtle, but it is profound. In modern megaprojects, scaling introduces new error classes because materials and reference systems interact dynamically. Steel expands, concrete creeps, soil settles. Human scheduling compresses timelines and compounds risk. In the pyramid, the foundation is partially carved into limestone bedrock. It is less a structure placed upon Earth than a geometry embedded within it. That choice alone may have eliminated entire categories of scaling instability. And here the contradiction sharpens. We possess supercomputers capable of simulating wind vortices around skyscrapers. We deploy satellites to correct positioning within centimeters. We analyze resonance modes before bridges open. And yet our largest projects often wobble, leak, or exceed tolerance predictions. 3,500 years before Christ, a civilization without iron tools preserved angular coherence across 13 acres of stone. This is not an argument for mystical knowledge. It is an invitation to examine constraint. Perhaps scaling fails when complexity increases faster than reference stability. Perhaps scaling succeeds when the reference frame is so disciplined that new error classes never emerge. Which raises the deeper question: was the Great Pyramid a monument, or was it a demonstration of controlled scale? What do you think about this? If geometric precision can hold across magnitude without modern correction systems, then the secret is not hidden machinery. It is foundational philosophy, and that philosophy begins at ground level. So we arrive at the central tension of this journey. Why does geometric precision degrade in modern megaprojects, but not here? Was it an accident, lost science, or a method so simple, so constraint-driven, that scale itself became obedient? To answer that, we must descend, not upward toward the summit, but downward, into the baseline, because if the secret exists, it will not be found in the height. It will be found in the first line drawn upon stone. What happens when we examine the baseline itself? Before a single block was lifted, before angles were sighted against the horizon, before 2.3 million stones began their ascent into geometry, something quieter happened. A line was drawn, not in ink, not in theory, but into the earth itself. We tend to think of the Great Pyramid of Giza as rising from the desert, but it does not simply sit upon sand. It is anchored into a limestone plateau, a geological formation that predates the pyramid by millions of years. The Giza Plateau is not soft sediment, it is Eocene limestone bedrock, dense, relatively stable, and capable of being cut, shaped, and integrated into architecture. That geological choice is not incidental. It is foundational. Excavations and mapping conducted by Mark Lehner and the team at Ancient Egypt Research Associates reveal that the pyramid's builders did not simply level sand and build upward. They cut into the bedrock, they carved trenches, they removed high points, they integrated a natural limestone knoll into the pyramid's core. In other words, they did not impose geometry onto unstable ground. They extracted geometry from stability. This distinction is critical, because when engineers today design megastructures, one of the greatest uncertainties lies beneath them. Soil compresses, clay shifts with moisture, bedrock fractures unpredictably, differential settlement, where one part of a foundation sinks slightly more than another, introduces angular distortion that compounds upward. A deviation of a few millimeters at the foundation can become centimeters at the roof line. In tall buildings, it becomes meters of stress redistribution. Modern engineers combat this with piles driven deep into substrata, concrete rafts, seismic isolation systems, and continuous digital monitoring. They model soil mechanics with complex computational simulations. Yet beneath the Great Pyramid lies something far simpler. Rock, carved flat. Evidence suggests that perimeter trenches may have been cut into the bedrock to establish a level reference. This idea was first proposed by Flinders Petrie in the 19th century. He hypothesized that the builders could have filled shallow trenches with water to create a gravitationally defined level plane. Water seeks equilibrium. Its surface is always perpendicular to the direction of gravity. If such trenches were used, the builders would have possessed something extraordinary for the Bronze Age, an absolute reference. Gravity does not drift. It does not expand with temperature. It does not fatigue. It does not depend on calibration. A water surface is not an instrument subject to error in the conventional sense. It is physics itself revealing level. Contrast this with modern leveling systems. Laser levels must be calibrated. Digital theodolites must be aligned. GPS coordinates require satellite synchronization and atmospheric correction. Steel measuring tapes expand and contract with temperature. Even electronic instruments introduce rounding errors. Every instrument drifts, and if the baseline drifts, everything derived from it inherits distortion. This is how entropy enters construction, not dramatically but incrementally. Imagine a base that is slightly out of level. Every block placed upon it compensates locally. Minor adjustments accumulate. The structure may appear coherent, but hidden stresses grow. Angles deviate. Load distribution becomes uneven. Scaling magnifies the misalignment. But if the initial reference plane is defined by gravity itself, if it is physically constrained rather than numerically approximated, then the opportunity for baseline drift diminishes radically. The base of the Great Pyramid is level within a few centimeters across roughly 230 meters per side. That is approximately 13 acres of surface, constrained to near planarity, without concrete, without steel, without electronic measurement. How does one achieve that? Not by speed, not by improvisation, but by eliminating uncertainty at the start. There is a concept in systems theory known as entropy control. Entropy, in this context, refers to the natural tendency of systems toward disorder. In construction, disorder emerges as cumulative error. Small inaccuracies propagate, minor misalignments amplify, correction mechanisms become necessary. But the most efficient way to control entropy is not correction. It is prevention. By carving directly into bedrock, the builders removed one entire class of instability, soil settlement. By potentially using water as a leveling reference, they removed instrument drift. By establishing a planar foundation across the entire footprint before large-scale stacking began, they ensured that subsequent geometry inherited coherence. Consider how modern megaprojects unfold. Foundations are poured in segments. Sections are constructed in parallel. Deadlines compress sequences. Survey teams recalibrate constantly as conditions change. Even with modern precision tools, alignment across large distances demands continuous adjustment. Correction becomes routine. The pyramid, by contrast, suggests a different philosophy. Stabilize once, propagate thereafter. If the baseline is gravitationally defined, then perpendiculars derived from it inherit stability. If right angles are constructed physically from a stable line, they do not accumulate angular drift randomly. The baseline becomes a constraint, and constraint is a form of discipline. There is also the geological advantage of the plateau itself. Limestone bedrock offers low compressibility relative to soil. Differential settlement becomes negligible. The structure's immense mass is distributed across material that resists deformation. Modern skyscrapers, even those founded on bedrock, must account for variable strata and dynamic loading. Wind-induced sway redistributes forces. Temperature cycles expand and contract steel frames. The pyramid's mass, by contrast, compresses uniformly downward, stone upon stone, gravity acting consistently over millennia. Here, gravity is not merely a force acting on the structure.
It is the reference that defined it.
And this introduces a philosophical inversion. In modern engineering, we often fight gravity, counteracting it with tension systems, reinforced materials, and active stabilization. In the pyramid, gravity appears to have been embraced as the organizing principle. If the initial level plane was defined by water in trenches, then the builders aligned their architecture with the most stable constant available on Earth. No recalibration required. No digital correction, no software patch. This would explain why the base does not exhibit large-scale warping. It would explain why corner angles remain coherent across 230 meters. It would explain why geometric relationships do not appear to degrade proportionally with size. Because the most dangerous source of scaling error, baseline instability, was constrained at the beginning. Every structure is only as stable as its first line. Modern megaprojects frequently encounter new classes of error precisely because scaling introduces variables that were not dominant at smaller size. Soil mechanics becomes unpredictable. Material behavior shifts. Thermal expansion magnifies. But if the foundation is physically inseparable from geological stability, and if the level reference is gravitationally anchored, then scaling becomes simpler.
Not easy,
but constrained. This is not mysticism, it is method. And it forces a quiet question. If the Egyptians established a gravitationally defined baseline before construction escalated, if they eliminated reference drift before the first course of stone rose, did they remove the most dangerous source of geometric entropy at the start? If so, then what appears miraculous at scale may in fact be the consequence of a single disciplined decision made at ground level. And if that is true, then the real achievement of the pyramid is not its height. It is its first perfectly level line. If you're finding this exploration of ancient precision and modern complexity meaningful, consider subscribing. There is much more beneath the surface, and what we uncover next will only deepen the mystery. If the real achievement of the pyramid is its first perfectly level line, then the next question becomes unavoidable. What happens when you turn that line 90 degrees? Because leveling solves only one dimension of stability. To transform a flat plane into a square, you must introduce angle, and angle is far more dangerous than height. A line can drift slightly and remain unnoticed. A right angle, if imperfect, betrays itself everywhere. At the corners of the Great Pyramid of Giza, the deviation from a perfect 90 degrees has been measured with extraordinary care. In the 1880s, Flinders Petrie conducted the first precision survey of the pyramid's geometry. Later refinements by surveyor Joseph Dorner confirmed something astonishing. The corner angles deviate from perfect right angles by roughly 45 arc seconds. 45 arc seconds. To understand the magnitude of that statement, we must translate it. 1 degree is divided into 60 arc minutes. 1 arc minute is divided into 60 arc seconds. 45 arc seconds is 45 over 3,600 of a degree. That is 0.0125 degrees. Across a base length of approximately 230 meters, such a deviation corresponds to only a few centimeters of angular discrepancy. Now consider what that means. If you misplace a right angle by even 1/10 of a degree at the start of a 230-meter baseline, the error compounds dramatically as you extend the sides. The longer the line, the greater the displacement at its end. Angular error is multiplicative. This is why modern survey teams use digital theodolites and GPS-based alignment systems, because small angular inaccuracies explode across distance. And yet here the explosion never occurs. So how did they construct right angles without trigonometry, without sine tables, without algebra, without numeric abstraction? The answer may lie not in numbers, but in geometry itself. Jean-Pierre Clerc, writing in the Journal of Ancient Egyptian Architecture, proposed a reconstruction known as the ATMR method, combined with extended perpendicular construction. Rather than calculating angles numerically, the builders could have used fixed-length rods to construct isosceles triangles physically on the ground. Imagine this. You begin with a straight baseline. From its center point, you measure equal lengths outward along the line. Then, using rods of identical length, you swing arcs that intersect at a point above the line. Connect that point back to the center. You have constructed a perpendicular, not by calculation, by symmetry. This is geometry embodied. An isosceles triangle enforces equality by construction. If the two sides are physically equal, the angle they enclose is constrained. There is no rounding error, no decimal approximation. You are not computing 90 degrees, you are creating it. Clerc's analysis suggests that such geometric propagation methods would predict angular deviations in the range of roughly 35 to 45 arc seconds, remarkably close to what Petrie and Dorner measured. In other words, the measured imperfection matches the expected physical limitations of rod-based geometry. This is not coincidence, it is fingerprint. Because geometric construction methods behave differently from numeric methods. In numeric abstraction, error enters through approximation. A measurement is taken, a value is recorded, it is used in calculation. Each step introduces rounding, transcription, or instrument uncertainty. In physical geometry, relationships are enforced spatially. Equal lengths remain equal because they are the same object. A rod does not forget its length between measurements. A perpendicular derived from intersecting arcs inherits symmetry directly. If your baseline is stable, level, straight, and carved into bedrock, then perpendiculars derived from it using fixed rods do not accumulate random angular drift. They inherit the stability of the original line. Angular error in this system does not multiply arbitrarily. It is constrained by the consistency of the measuring unit. This is a subtle but profound difference. Modern engineering often relies on hierarchical abstraction. Design occurs in numerical space. Construction attempts to realize those abstractions in physical space. Correction systems reconcile discrepancies. In the pyramid's case, design and execution may have been unified in physical geometry. There is no translation between number and stone. The geometry exists directly in the ground before it exists in the structure. The right angle is not a computed concept. It is a constructed event, and because it is constructed from equal lengths and stable baselines, its error is bounded. Consider the danger of angular propagation. If one corner were misaligned by even a small fraction beyond tolerance, the opposite corner would not close neatly. The square would distort into a rhombus. The sides would differ significantly in length. The apex would drift off-center. Yet the measured differences in side lengths are under 20 centimeters across 230 meters. That is less than 1 part in 1,000. This suggests not only angular discipline but closure verification. The builders likely checked diagonals. In a square, equal diagonals confirm right angles. If the diagonals matched within tolerance, the square held. Again, no trigonometry required, only rods, only repetition, only constraint, and this may explain why angular error does not appear to grow catastrophically with scale. Each perpendicular derived from the baseline is re-anchored to the original reference. Error does not cascade unchecked, it is reset by symmetry. Modern large-scale construction often extends grids outward sequentially. Small misalignments propagate through cumulative measurements. Correction occurs periodically, but drift can enter between calibration points. In a physically constrained geometric system, the shape enforces its own correction. The square demands closure. The diagonal verifies equality. The rod maintains unit consistency. There is something almost architectural about this method, not in the sense of buildings, but in the sense of logic. Geometry becomes a discipline of constraint rather than approximation. And yet, even if right angles were constructed with extraordinary care, one final variable remains. Orientation. A square can be perfectly square and still be rotated incorrectly. The Great Pyramid is not merely square. It is aligned to true north within 3 to 4 arc minutes. That level of precision introduces a new layer of complexity. Constructing right angles without numbers is one challenge. Locking those angles to the rotational axis of the planet is another entirely. If they derived perpendiculars physically from a baseline, how did they determine the direction of that first line? How did they ensure that their initial axis corresponded not to magnetic north, not to a local landmark, but to the Earth's rotational pole? Because if angular propagation was disciplined, then the origin of that propagation becomes the true mystery. How did they lock cardinal north so precisely? To ask that question is to step outside architecture and into astronomy. Because a right angle on the ground is one achievement, but aligning that angle to the rotational axis of the Earth, without compass, without clock, without telescope, is something else entirely. The Great Pyramid of Giza is aligned to true north with an error of roughly 3 to 4 arc minutes. That is approximately 0.05 degrees. To put that into perspective, if you extended one face of the pyramid for a full kilometer, its deviation from true north would be less than a meter. This was measured first by Flinders Petrie, refined by Joseph Dorner, and statistically reconstructed by Glenn Dash. 3 to 4 arc minutes. Without a compass. And here we must clarify something critical. Magnetic north is not true north. A compass aligns to Earth's magnetic field, which drifts over time and deviates significantly from geographic north depending on location. The ancient Egyptians did not possess magnetic compasses. Even if they had, magnetic declination would have introduced significant error. The pyramid is aligned not to magnetism, but to the rotational axis of the planet. This is astronomical north. Determining it requires observing the sky. There are two leading classes of explanation. The first is stellar. Kate Spence proposed that the Egyptians may have used a pair of circumpolar stars, possibly Kochab in Ursa Minor and Mezar in Ursa Major, observing the moment when they formed a vertical alignment in the sky. When the line connecting them was perpendicular to the horizon, that vertical plane would approximate true north. Astronomer Clive Ruggles and others have examined stellar alignment models extensively. The advantage of stellar methods is that circumpolar stars never set. They rotate around the celestial pole nightly. If you track their upper or lower culmination, their highest or lowest points in the sky, you can approximate north with surprising precision. However, there is a complication: astronomical drift. Earth's rotational axis wobbles slowly over approximately 26,000 years in a motion known as axial precession. This means that the position of the celestial pole relative to background stars changes gradually. The star we call Polaris today was not the pole star in 2500 BC. If stellar alignment was used, the specific star pair and the date of construction must align precisely with precessional models. Spence's hypothesis intriguingly correlates pyramid orientation error with estimated construction dates. But there is another possibility. In 2016, Glenn Dash conducted a simple but profound experiment in Pomfret, Connecticut. On the autumnal equinox, he placed a vertical rod, a gnomon, into level ground. Throughout the day, he marked the tip of its shadow at regular intervals. When the sun crosses the equator on an equinox, the path of the shadow traces an almost perfectly straight east-west line. Perpendicular to that line lies true north-south. Dash demonstrated that this equinox method produces alignment errors similar in magnitude and direction to those measured at the Great Pyramid, including a slight counterclockwise deviation shared by the pyramids of Khufu, Khafre, and even the earlier Red Pyramid of Sneferu at Dahshur. This is remarkable, because it suggests the alignment may not have required stars at all. It may have required patience. The equinox can be determined by counting approximately 91 days after the summer solstice. The sun rises due east and sets due west only on 2 days each year. By tracking the shadow carefully and plotting its path, a straight line emerges, not from abstraction, but from observation. And again, gravity and light become references. The rod stands perpendicular because of gravity. The shadow line is defined by solar geometry. The Earth itself provides the axis. In modern surveying, orientation to true north is achieved using GPS satellites. Receivers triangulate position relative to multiple orbital signals. Atmospheric correction models refine location. Orientation can be achieved within centimeters and fractions of degrees rapidly, but it requires electronics, atomic clocks, and orbital infrastructure. The pyramid required sky and time. Here is the statistical tension. To align a structure accidentally to within 4 arc minutes of true north is astronomically improbable. Random orientation across 360 degrees would yield an average error of 180 degrees. Even constrained by cardinal intention, achieving sub-degree precision without systematic method is unlikely.
Yet the alignment is not unique to Khufu's pyramid. The Pyramid of Khafre, slightly smaller but adjacent, shares similar precision. The Red Pyramid of Sneferu, father of Khufu, also demonstrates remarkable cardinal orientation.
Moreover, all three exhibit a slight counterclockwise deviation from true north. This is critical. If each pyramid were aligned independently by chance, the errors would scatter randomly, some clockwise, some counterclockwise. Instead, they cluster. This suggests a consistent method, a systematic approach that introduced a predictable bias. Dash's equinox experiment reproduced a counterclockwise deviation under certain conditions of solar observation. Stellar alignment models can also predict systematic bias depending on star selection and timing. The shared error becomes evidence of technique, and this is where scaling meets astronomy. Because once the initial north-south axis was determined with precision, every perpendicular derived from it inherited planetary alignment. The square was not merely square, it was planetary. This alignment transforms the pyramid from local architecture into geodetic instrument. Its faces are not arbitrary orientations. They are anchored to Earth's rotational geometry. And yet something changes in later dynasties. Subsequent pyramids do not consistently maintain this extreme precision. Deviations increase. Cardinal alignment becomes looser. The methodological rigor appears to soften. Why? If the technique was known, why was it not preserved indefinitely? Did political instability erode institutional knowledge? Did astronomical methods shift? Did religious symbolism replace geometric obsession? Or was the extreme precision of the Fourth Dynasty a deliberate experiment rather than a permanent standard? The alignment of the Great Pyramid is not mystical, it is measurable. But it sits at the intersection of astronomy, geology, and geometry in a way that suggests unusual intentionality. The builders were not simply stacking stones toward the heavens, they were orienting stone to the rotation of a planet. And this returns us to the deeper pattern emerging. Level defined by gravity, right angles defined by symmetry, orientation defined by celestial motion. Each reference is invariant. Each is external to human error. Gravity does not drift. The Earth's axis rotates predictably. The Sun crosses the equator on schedule. If the builders anchored their geometry to these constants, then scale becomes obedient not because they eliminated physics, but because they aligned themselves with it. And yet the lingering question remains. If they possessed a method capable of such astronomical precision, why did that precision diminish in later generations? What changed? And what does that tell us about the fragility of disciplined knowledge? The planetary alignment and geometric control establish a macro-scale framework. But the true test of discipline lies not in the overall form, it lies in the joints. When Flinders Petrie conducted his late 19th century survey of the Great Pyramid of Giza, he recorded something extraordinary about the surviving casing stones. The outer casing is largely gone today, stripped in later centuries, but fragments remained in situ at the base and others were recovered. Petrie measured joint gaps averaging around 0.5 millimeters. In some instances, he reported even tighter contact. Half a millimeter, that is thinner than a fingernail. This was not rough stacking, it was precision masonry. One of the most important surviving pieces is often referred to as the Edinburgh casing stone, now housed in the collection of the National Museum of Scotland. It preserves the smooth, angled face and finely dressed bedding surface characteristic of the original casing. When examined closely, the contact surfaces show deliberate finishing, not casual dressing. The stone faces were not only flat, they were planar across their entire contact length. The casing material itself matters. The builders used fine-grained limestone quarried from Tura, east of the Nile. Tura limestone has a tight crystalline structure and homogeneous texture, allowing it to be cut and polished to a high finish. Unlike coarse limestone, which fractures unpredictably, this material supports controlled abrasion and smoothing. When freshly cut, it is relatively soft, hardening upon exposure. The polishing technique appears to have involved abrasion rather than only impact cutting. Copper chisels, while relatively soft compared to modern steel, can shape limestone effectively when frequently resharpened. Dolerite pounders, dense hard stone tools, were used to rough out surfaces, but achieving sub-millimeter contact across large bedding planes required something more than pounding. It required repeated testing of contact, incremental correction, and controlled abrasion, likely with fine sand acting as a grinding medium. Here, the distinction between microscale and macroscale becomes critical. Macroscale refers to the full structure, 230 meters per side at the base, rising originally to about 146 meters. Microscale refers to the contact between individual stones. The paradox is that the macro-scale stability depends entirely on micro-scale discipline. If individual stones vary unpredictably in dimension or surface flatness, errors accumulate vertically and laterally. Slight angular deviations at each course would translate into measurable distortions across dozens of layers. Yet the pyramid's faces remain remarkably flat. This implies that stone dimensions were not random. They were controlled within tolerances that prevented cumulative drift. When casing stones meet with joints of approximately 0.5 millimeters, the interface itself becomes self-correcting. Large irregularities simply cannot be accommodated. A protrusion forces reworking. A hollow creates instability. The demand for tight contact enforces uniformity. Micro-precision constrains macro-error. And micro-precision requires standardized units. If each mason measured independently using variable reference lengths, even slight inconsistencies would compound. Consider a hypothetical deviation of just 2 millimeters per block in horizontal dimension. Across 200 blocks in a row, that becomes 40 centimeters of error. Across 4 sides, asymmetry becomes unavoidable. Yet the base lengths of the Great Pyramid differ by only a few centimeters overall. The implication is unavoidable. Dimensional control existed at the level of individual stones. This does not require metal rulers in the modern sense, but it does require repeatable measuring devices. Wooden cubit rods are known from later Egyptian contexts. Some surviving examples are subdivided into palms and digits with consistent spacing. Even if perishable materials have not survived from the 4th dynasty, the logic of the construction suggests comparable standardization. Tool limitations actually strengthen this conclusion. Copper chisels deform quickly. Dolerite pounders deliver force, but not fine calibration. These constraints mean that precision could not rely solely on cutting accuracy. It had to rely on measurement discipline. Stones were likely rough-shaped, then repeatedly checked against straight edges, plumb lines, and leveling surfaces before final placement. A plumb line uses gravity as its reference. A straight edge tests planarity directly. When two stones are rubbed together with abrasive sand, high spots reveal themselves. Each of these methods uses physical reality as a constraint rather than abstract calculation. Poor unit control would have amplified error at the macro scale long before the structure reached significant height. Misaligned courses would create visible lean. Uneven casing would distort the intended smooth faces. Instead, the casing appears to have formed continuous planes, reflecting sunlight almost like polished shell. Microscale discipline is not decorative refinement, it is structural logic. The casing stones were not merely aesthetic coverings. They locked the geometry. Their precision implies that dimensional standards were shared, taught, and enforced across teams. It suggests that measurement was not approximate but institutional. And that brings us to a deeper question. If they achieved such consistent dimensional control without hardened metal rulers or surviving standardized gauges, how were their units stabilized across thousands of workers and decades of construction? This whole discussion is telling us our ancestors were really genius. What do you think about this? The question of standardized units leads directly into the science of metrology, the control of measurement itself. Monumental precision cannot exist without a stable unit. In ancient Egypt, that unit was the royal cubit. Archaeological finds from later periods preserve wooden and stone cubit rods divided into 7 palms, each palm subdivided into 4 digits, for a total of 28 digits per cubit. The length of the royal cubit averages about 52.3 centimeters. While surviving rods date primarily to the New Kingdom, their consistency implies a long-established tradition. Measurement in Egypt was not improvised, it was formalized. But wood expands and contracts, humidity alters length, wear changes edges. If the Great Pyramid required dimensional stability across 230 meters, how could perishable rods maintain accuracy? The answer may lie in redundancy and calibration. Unlike flexible cords, rods resist elastic deformation. A cord under tension can stretch significantly. Experimental reconstruction suggests that plant fiber ropes may stretch up to around 2% under load. Over a 100-meter baseline, that could introduce a 2-meter discrepancy if not carefully managed. Even at lower loads, fractional elongation accumulates unpredictably. Temperature and moisture exacerbate the variability. Rods, by contrast, provide discrete, rigid units. When multiple rods are placed end-to-end, a rod linkage system, cumulative error can be minimized by periodic recalibration against a master reference. If the master rod was stored in a controlled environment and used to verify working rods regularly, dimensional drift could be contained. Modern surveyors face similar issues. Steel tapes expand with temperature. A 50-meter steel tape can lengthen several millimeters between cool morning and hot afternoon. Precision survey work requires temperature correction factors. The Egyptians would not have calculated coefficients of thermal expansion, but they may have intuitively mitigated variability by measuring during stable environmental conditions or cross-checking between teams. There is also iconographic and textual evidence that measurement was ritualized. The stretching of the cord ceremony, known as pejishes, appears in temple reliefs, where the king and a deity jointly hold a cord to lay out a sacred structure. This scene is not mere symbolism. It encodes the cultural importance of establishing axes and boundaries through measured tension. However, the cord alone would not define final dimensional control. It would establish orientation and broad layout. Fine control required rigid standards. Instruments such as the Merket, essentially a sighting tool used with a plumb line, allowed alignment with stars. The bay, a form of sighting rod, could assist in establishing straight lines across distance. These were simple devices, yet when used repeatedly and in coordination, they provided consistent reference. An inscription from the reign of Kasekemwi references construction and boundary establishment in terms suggesting organized planning and state oversight. By the time of the Fourth Dynasty, measurement was embedded within administrative authority. Quarry marks inside the Great Pyramid of Giza reference work crews with defined identities, implying coordinated labor rather than ad hoc craftsmanship. Metrology, then, was not just technical, it was institutional. If the royal cubit was defined once and copied carefully, and if teams worked from rods derived from a master standard, scaling becomes predictable. A base of 440 royal cubits per side, the widely accepted dimension of the Great Pyramid's original design, produces a square of approximately 230.3 meters. The height of 280 cubits yields the well-known geometric ratio approximating 14:11 between half base and height. Whether that ratio was symbolic or practical, it demonstrates that dimensions were not arbitrary. They were multiples of a stable unit. Measurement discipline acts as a control system. If one team sets foundation lines using calibrated rods, and another shapes casing stones to integer cubit fractions, dimensional compatibility is enforced automatically. Deviations beyond tolerance would be visible immediately when rods failed to align or courses failed to meet. In modern engineering, scaling errors often originate not from calculation mistakes, but from inconsistent reference standards. A miscalibrated instrument can propagate error across an entire project. The Egyptians appear to have minimized this risk by anchoring their construction to physical standards repeatedly verified in practice. And yet the scale of the enterprise raises an intriguing possibility. Was this merely construction, or was it also a test bed for refining measurement itself? The Fourth Dynasty pyramids represent a peak of geometric precision not consistently matched in later periods. That suggests either an extraordinary concentration of expertise or a deliberate emphasis on experimental exactitude during this era. If the Great Pyramid embodies 440 cubits per side with astonishing consistency, it may reflect not only architectural ambition, but metrological refinement at a national scale. When a civilization builds at planetary alignment, sub-millimeter stone contact, and cubit-level proportional harmony, measurement ceases to be background utility. It becomes the foundation of power, which leads to an unsettling thought. Were they simply building in stone? Or were they perfecting a system of measurement capable of controlling scale itself? When we consider the challenges of scaling, modern engineering offers a sobering lesson. Even with advanced computation, steel, concrete, and sophisticated monitoring, the larger the structure, the more complex the interaction of forces, materials, and environmental variables. In skyscrapers, bridges, and tunnels, small errors are amplified by non-linear laws of physics. The Millennium Bridge in London provides a clear example. Opened in June 2000, this pedestrian bridge, designed with state-of-the-art engineering and architectural flair, famously exhibited lateral resonance instability. Thousands of pedestrians crossing the bridge induced a synchronized sway, a phenomenon now known as synchronous lateral excitation. The bridge oscillated enough to alarm users, prompting its closure just 2 days after opening. Modern analysis revealed that the designers had underestimated the interaction between the footfalls of thousands of individuals and the natural frequencies of the structure. The feedback loop emerged spontaneously, a classic non-linear response. Small disturbances multiplied into a macroscopic effect. Despite calculations, modeling, and high-quality materials, dynamic forces had been underestimated. The Big Dig in Boston presents a more prosaic, yet equally instructive, failure of scaling and system integration. One of the most expensive urban infrastructure projects in history, the Central Artery/Tunnel project, faced extraordinary challenges. Subsurface alignment of tunnels beneath an existing dense urban network demanded precise surveying and tunneling. Yet water leakage became a persistent problem, attributed to misaligned tunnel segments, compromised waterproofing membranes, and unpredictable soil-water interactions. Concrete, steel, and protective coatings behave differently under long-term load and exposure to groundwater. Settlement, differential compaction, and thermal expansion all contributed to stress on joints, leading to cracking and leakage. What was intended as a continuous, smooth infrastructure system became riddled with discontinuities. Engineers had to retrofit solutions, inject grout, and introduce monitoring networks. Here, the scaling issue was not just size, but multiplicity of interacting variables: ground composition, existing foundations, concrete curing, water pressure, and construction sequencing all generated error classes that grew with system complexity. Thermal expansion is another invisible adversary. Consider steel structures, whether bridges or high-rise buildings. Steel expands approximately 12 parts per million per degree Celsius. For a 500-meter bridge span, a temperature differential of 30 degrees could cause a longitudinal expansion of almost 18 centimeters. Expansion joints and bearings are carefully engineered to absorb these movements, but errors in calculation, misalignment, or improper material selection can generate stresses that propagate into deflection, fatigue, and vibration. In skyscrapers, temperature variation between sun-exposed and shaded facades can induce twisting or bowing. Even differential cooling of poured concrete segments introduces minor angular deviations that, over hundreds of meters, can accumulate into measurable misalignment. Differential settlement compounds the problem. Skyscrapers rely on foundations that distribute enormous loads to the subsurface. No soil is perfectly uniform. Variability in compressibility, moisture content, and pre-existing stresses can cause one side of a building to settle slightly more than the other. For ordinary structures, a few millimeters may be tolerable. For megastructures, slight differential settlement translates into angular drift, stress concentrations, and potentially catastrophic structural fatigue. Even when buildings are founded on bedrock, stratification, fault lines, or weathered layers introduce asymmetry. Engineers model these effects using complex simulations, but every model is an approximation. Soil mechanics, while sophisticated, remains inherently probabilistic. Modern construction faces an additional complication: cumulative error propagation. In sequential building methods, each segment or course relies on the previous one for reference. Even with laser alignment and digital instruments, tiny deviations from nominal measurements are unavoidable. These errors propagate non-linearly, especially over distances where minor angular misalignment leads to meter-scale deviation at the extremities. Non-linear scaling laws, familiar in physics and engineering, dictate that error does not increase linearly with size. It increases according to more complex relationships, often proportional to square or cubic factors depending on the type of deformation, vibration, or environmental influence. What is insignificant at a 10-meter scale becomes significant at 100 or 500 meters. Entropy provides a useful framework for understanding this. In systems theory, entropy represents disorder, the accumulation of small deviations, uncertainties, and unpredictable interactions. In megaprojects, every joint, every measurement, every interface contributes to system entropy. Thermal movement, material fatigue, imperfect installation, and human error all inject disorder into the system. Feedback loops, such as the pedestrian-induced oscillation of the Millennium Bridge, amplify this disorder. Settlement in tunnels or foundations introduces hidden stress, potentially propagating cracks and leaks. Error classes are multidimensional: angular, linear, thermal, vibrational, and material-specific, all interacting non-linearly. The larger and more complex the system, the more entropy accumulates. Contrast this with the Great Pyramid. Its foundation is carved directly into limestone bedrock, offering a remarkably stable base. Unlike soil-dependent modern megastructures, the pyramid is seated on a material that does not compress or creep appreciably over millennia. This geological constraint eliminates an entire class of error before construction even begins. Differential settlement, the bane of skyscrapers and tunnels, is virtually absent. Thermal expansion, while present, has negligible effect on massive limestone blocks compared with steel spans. The bedrock integrates with the geometry, creating a baseline resistant to non-linear propagation of error. Furthermore, the construction sequence in the pyramid differs fundamentally from modern methods. Instead of multiple independent crews working in parallel with segmented references, the pyramid's design may have used physically enforced geometries, baseline lines, perpendiculars, and leveling planes, derived from invariant references such as gravity and stellar orientation. Each subsequent block inherits the constraints of the first courses. Minor deviations are mechanically corrected through the interface of stone-to-stone contact rather than digitally or administratively. Micro-precision, as seen in the casing stone joints, translates into macro-scale geometric discipline. Unlike modern megaprojects, where correction occurs after deviation is detected, the pyramid constrains deviation in real time through physical laws. Error classes in modern projects illustrate the multiplicity of challenges that ancient builders avoided through constraint. Lateral resonance in bridges, settlement-induced misalignment in tunnels, thermal expansion-induced stress in steel, differential soil compression in skyscrapers. These are all non-linear error sources that interact unpredictably. Each dimension of uncertainty can amplify others, producing emergent instability. In physics, such non-linearities often follow power laws. Doubling the scale does not double the risk, it may increase it tenfold or more. The Millennium Bridge's oscillations arose because a nominally minor dynamic effect multiplied under pedestrian synchronization. The Big Dig's water leakage reflects multiple interacting subsurface uncertainties, compounded by imperfect sequence control. Modern steel structures must actively accommodate expansion and contraction. Miscalculations can lead to fatigue fractures. In contrast, the pyramid's approach appears anticipatory rather than reactive. By anchoring to bedrock, establishing level baselines, constructing right angles through physically enforced methods, and standardizing units through metrology, the builders constrained error before it could propagate. Entropy is controlled not by correction, but by prevention. Nonlinear amplification is minimized because primary variables, the baseline, the angles, the unit lengths, are physically constrained and integrated into the design. Every subsequent measurement or placement derives from stable references. This does not suggest the builders were immune to error. Blocks vary slightly, joints have minor gaps, and the apex does not align perfectly with the base center. But the deviations are orders of magnitude smaller than would be expected if standard soil foundations, flexible measuring tools, and uncoordinated crews were used. Where modern engineering struggles with unpredictable error propagation, the pyramid demonstrates the power of disciplined constraint applied at the outset. The comparison highlights a fundamental principle. Scaling is not simply a matter of size, it is a matter of error management. Modern megaprojects often face unpredictable environmental and material variability that increases with scale. The pyramid's success suggests that embedding constraints at the foundation, using invariant references, and enforcing physical discipline in measurement and placement can suppress the non-linear amplification of error. It raises a compelling question. Were the Egyptians consciously designing for stability at scale, understanding, even if not in abstract terms, the principles of nonlinear propagation and entropy control, or did their methods emerge experimentally, refined over generations as they discovered which constraints prevented catastrophic deviation and which did not? Whatever the case, the Great Pyramid remains a striking outlier. Modern projects with advanced tools, engineering software, and decades of accumulated knowledge continue to experience challenges that the pyramid seems to have avoided naturally. Its integration with the plateau, its reliance on physical measurement standards, and its disciplined geometric propagation create a structure that resists the error classes that modern engineers struggle with. The pyramid does not merely endure, it endures without sophisticated instrumentation, without steel reinforcement, and without electronic monitoring, precisely the challenges that in contemporary contexts magnify error and unpredictability. The lesson emerges not in materials or technology alone, but in the philosophy of constraint, discipline, and the early suppression of entropy. Non-linear instabilities are unavoidable in most large-scale systems, yet by anchoring the system to invariant references and controlling units at every scale, the Egyptians appear to have created a structure where error could not multiply unchecked. In modern terms, the Great Pyramid anticipates systems theory, error propagation models, and the critical importance of reference stability, all without recourse to modern abstraction. The question lingers: did these builders understand empirically or intuitively the principles that today we model mathematically? Or did they simply discover through iteration and institutional knowledge the constraints necessary to prevent non-linear instability? The pyramid stands as evidence that controlling the foundation, the geometry, and the units can suppress error propagation in ways that even today challenge engineers. And in doing so, it provides a blueprint not only for architecture, but for understanding the discipline required to scale with precision across space and time. The previous discussion on error propagation highlights a profound distinction between modern construction and the methods employed at Giza. Modern towers, bridges, and tunnels rely on foundations that are themselves subject to the caprices of the environment. Soil compresses, swells, or shifts under load. Water infiltrates. Temperature and seasonal cycles subtly alter properties. Even when engineers employ pilings driven deep into strata or concrete rafts poured to distribute load, the foundation remains an active participant in the structure's behavior, a medium capable of introducing error. Settlement analysis, soil mechanics, and load distribution models attempt to predict these effects, but prediction is never perfect. Small variances in compressibility, uneven moisture content, or heterogeneity in strata produce differential settlement, which over decades manifests as tilting, cracking, or cumulative drift. The Earth in these cases is passive, an unstable partner in the construction process.
The builders of the Great Pyramid of Giza approached the foundation differently. The Giza plateau is underlain by fine-grained, thickly bedded limestone. This stone is dense, non-porous, and remarkably consistent in load-bearing properties. Importantly, the pyramid was not placed arbitrarily on the plateau. It was built around a naturally occurring limestone knoll, which rises slightly above the surrounding bedrock. Archaeological surveys show that the builders carved the base into the plateau itself, using natural contours where beneficial and leveling selectively to create a continuous plane. Rather than imposing geometry upon an unstable substrate, they integrated their design with the existing topography.
Carving the bedrock achieves several advantages. First, it provides absolute stability. Limestone at the surface has negligible long-term compression. Unlike soil, it will not deform appreciably under the pyramid's weight, even over millennia. Second, cutting into the knoll allows a consistent plane to be established, reducing the need to reconcile natural irregularities with artificial leveling. Third, the slight rise of the knoll may have provided gravitational drainage for surface water, protecting courses from erosion and seepage, a subtle but significant factor in long-term structural integrity. Modern engineering contrasts sharply. Foundations of contemporary skyscrapers often consist of massive poured concrete rafts or reinforced pilings. Concrete, though strong, behaves differently than intact bedrock. It shrinks and creeps over time. Pile systems transmit load into deeper strata, but rely on heterogeneous soil for support. Even the most carefully modeled soil-structure interaction cannot eliminate variance. Settlement analysis for high-rise towers typically accounts for differential compression between piles, local soil heterogeneity, and long-term consolidation. Engineers may expect a few centimeters of settlement over decades and design structural tolerances accordingly. The process is probabilistic. The foundation is part of the system, but it is not perfectly predictable. The pyramid, by contrast, creates a foundation coupled with the earth itself. Bedrock is not an approximation, nor is it modeled probabilistically. It is a constraint. A stone interface of predictable rigidity anchors every course above it. The macrogeometry of the pyramid is no longer independent. It is mechanically integrated into the substrate. Each line, each right angle, each block of the base is referenced directly to a stable plane that does not shift over centuries. Gravity acts not only on the structure but through it, transmitting force into a medium that will not deform under its weight. The effect is to remove an entire class of error from the system: foundation instability. This integration also impacts scale. In modern construction, errors from foundation settlement amplify in proportion to height. A skewed or uneven base causes angular deviations that propagate upward. Small discrepancies in soil stiffness or compaction create differential stress along the superstructure. In high-rise construction, this can be mitigated with flexible joints, tensioned cables, or active monitoring. In the pyramid, these risks are virtually eliminated. The first course, cut and leveled in bedrock, serves as a perfect anchor. Subsequent courses inherit the rigidity of this foundation. Micro-level precision in block placement is supported not only by measurement discipline, but by the stability of the medium beneath. Earth-coupled geometry also introduces feedback that a fully imposed geometry cannot replicate. If a horizontal plane is laid on deformable soil, leveling devices measure relative to an unstable reference. Minor depressions, rises, or shifts introduce residual error that may not be corrected fully, even with lasers or digital instruments. Carving into bedrock, however, ensures that the reference plane is invariant. Gravity defines true level. The plane is not theoretical, it is physically realized. Angular propagation, alignment, and orthogonality are all derived from a substrate that enforces constancy. This may be one of the most fundamental distinctions between ancient Egyptian megastructures and modern projects. Beyond the primary bedrock plane, the choice to build around a natural knoll further stabilizes load distribution. The pyramid's mass is concentrated over a slightly elevated core, which disperses vertical force more evenly. Minor irregularities in the limestone surrounding the knoll are cut to integrate seamlessly. This avoids concentration of stress at weak points, a common problem in artificial foundations. Modern practice often requires extensive geotechnical mitigation, soil replacement, compaction, or reinforcement to approximate this effect. The Egyptians achieved it passively by observing the terrain and adapting the base geometry accordingly. The integration with bedrock also interacts with thermal and environmental factors. Limestone's coefficient of thermal expansion is low relative to steel or concrete. Daily and seasonal temperature variations introduce minimal differential expansion. Rainwater runoff and erosion are mitigated by drainage channels and the knoll's slight elevation. In contrast, modern materials can expand and contract significantly, leading to cumulative deviations, if not mechanically compensated. Even at a conceptual level, the pyramid's foundation embodies a systems theory approach long before the term existed. The foundation is not a neutral platform. It is an active participant in maintaining structural integrity. By coupling architecture with geology, Error classes associated with shifting or deforming substrates are removed before they propagate. Angular deviations, cumulative settlement, and long-term creep are minimized because the structure rests upon an invariant reference. Each subsequent measurement, alignment, and placement draws from a foundation that is effectively eternal on human timescales. Modern analogues struggle with this principle. Engineers may attempt to create rigid artificial bases, but inherent variability in materials and the environment guarantees residual error. Reinforced concrete will shrink, piles will settle unevenly, steel will expand, and even geotechnical modeling cannot perfectly predict interactions. Errors accumulate, feedback loops emerge, and non-linear instabilities manifest, as seen in bridges, tunnels, and high-rise towers. The pyramid, by using the Earth itself as an integrated partner, avoids these complications. The choice to integrate construction with the bedrock may also explain durability. Millennia of exposure, wind, thermal cycles, seismic events of minor magnitude have caused only minimal distortion at the base. The Earth beneath absorbs and distributes forces, creating an inherently stable platform. The macrogeometry is preserved because the micro-level reference, the bedrock plane, remains consistent. There is no independent variable to drift. Thus, the foundation is not merely support, it is constraint. The pyramid's geometry obeys the Earth as much as the stones obey the cubit. The physical anchoring to the plateau suppresses an entire class of instability that modern engineers must actively monitor and compensate for. By carving the base into solid limestone and integrating the design with a natural knoll, the builders created a system where the substrate itself enforces geometric fidelity. The cumulative effect is profound. Leveling, angular propagation, alignment to cardinal points, and micro-precision in block placement are all amplified by the stability of the bedrock. Errors that would typically multiply with scale are physically constrained before they arise. Unlike modern foundations, which act as probabilistic participants in structural behavior, the bedrock acts as an invariant reference. Geometry and geology become a single, interdependent system. The question that emerges is subtle but consequential. Did anchoring to bedrock eliminate a whole class of error? Did the builders understand, intuitively or empirically, that by integrating their design with the Earth itself, they were removing unpredictable variables, stabilizing scale, and creating a structure that could resist millennia of environmental stress? By letting the planet itself become a participant in the construction process, the Great Pyramid achieves a level of stability and precision that modern megaprojects struggle to replicate, even with computers, steel, and sensors. The bedrock is not merely a foundation, it is a silent partner, a constraint, and perhaps the ultimate secret behind the pyramid's enduring geometry. Do you also agree with this? If we step back from the stones themselves and examine the Great Pyramid from a mathematical perspective, the magnitude of what was achieved becomes almost incomprehensible. Consider the base and height in relation to one another. The pyramid's original height was roughly 146.6 meters, and each side of the base measured approximately 230.3 meters. When these dimensions are compared, the ratio of perimeter to height aligns astonishingly closely with the constant now known to us as 2 times pi. The deviation is infinitesimal, less than 0.1%, around 0.04%. To achieve this by accident, by stacking blocks with no overarching design principle, would be statistically unlikely. Experts have calculated that the probability of reaching such a precise proportional relationship purely through chance is roughly 1 in 11, assuming uniform distribution of plausible block arrangements and ignoring the corrections that would have been required to maintain angle consistency across 4 massive sides. The improbability is compounded when we examine the angular precision. The corners of the base are right angles within approximately 45 arc-seconds. By contrast, the sides of the base are aligned with a discrepancy of less than 20 centimeters across 230 meters. Angular deviation is not simply a linear measure. It is an expression of coherence across the entire structure. Random stacking of blocks, even if each block were placed with careful attention, cannot produce this level of consistency. Small errors would accumulate across hundreds of courses, and the corners would drift noticeably from perpendicular. Statistical models show that even minute deviations in block size or placement propagate exponentially across the pyramid's footprint, yet the deviations at the Great Pyramid remain extraordinarily tight. Mathematical analysis of the pyramid's geometry has confirmed these patterns. Glenn Dash, in studies conducted in 2012 and 2015, applied linear regression techniques to reconstruct the pyramid's baseline and corner positions based on survey data. Regression allows one to account for minor errors in measurement while modeling the underlying intended geometry. When Dash and colleagues plotted the positions of the corners and baseline points, they found remarkable linear coherence. Variability in side length and corner placement clustered around predicted values with a narrow standard deviation, demonstrating statistical regularity rather than random scatter. The patterns of deviation are consistent with a disciplined geometric system rather than accidental placement. Furthermore, the relationship between corner angles and side lengths is revealing. The four corners are all right angles to within 45 arc seconds, yet the sides are matched with minimal difference across hundreds of meters. This is significant because maintaining right angles does not automatically preserve side length equality. Without a system of measurement and correction, angular fidelity and linear fidelity cannot coexist at this scale. The fact that both are maintained suggests a deliberate strategy for controlling error propagation. In statistical terms, the correlation between angular accuracy and side length consistency is far beyond what would be expected by chance. Random processes cannot create two independent variables that simultaneously fall within such tight tolerances over a structure of this size. The pyramid also demonstrates internal mathematical coherence. If one considers the sequence of courses and their height relative to the base, the slope of each face was maintained at approximately 51 degrees 51 minutes, a value consistent with the overall geometric proportions. Maintaining this slope across 210 courses with tens of thousands of individual blocks requires not only precise measurement, but also constant adjustment and verification. Each block placement had to account for both micro-level precision and macro-level geometry. Minor variations in height or horizontal displacement must have been corrected immediately, or cumulative errors would have disrupted the intended angles. Probability theory further illuminates the improbability of achieving this coherence randomly. If we model block placement as independent, identically distributed events with plausible variation based on tool and measurement limits, the likelihood of maintaining both right angles and uniform side lengths across the base diminishes exponentially. A single misplaced block could propagate angular error through subsequent courses, yet the deviations remain minuscule. In effect, the structure behaves as though guided by an underlying mathematical principle rather than the stochastic behavior of human labor alone. The perimeter-to-height ratio itself carries profound implications. That it approximates 2 times pi with such precision suggests a conceptual understanding of circular proportion, a knowledge that could have been empirical or derived from systematic observation and geometric abstraction. Combined with the corner angle fidelity, the height of the apex and the slope of the faces, the entire structure exhibits pattern coherence across multiple geometric dimensions simultaneously. Statistical models of chance placement cannot account for this multidimensional alignment. The convergence of these measurements is too tight, too consistent, to be attributed to luck alone. Regression analysis plays a central role in confirming these observations. By plotting the coordinates of surviving casing stones and reconstructed baselines, researchers can identify trends and deviations from nominal geometry. Dash's analysis shows that the deviations are not random, they follow predictable patterns that reflect intentional design. Minor deviations often appear systematic, suggesting either a controlled bias or adaptive correction during construction. This indicates that the builders were not merely reacting to errors, but anticipating them and integrating corrections into the ongoing process. In other words, the construction process itself enforced geometric coherence, producing statistical regularity across the entire pyramid. The interplay between scale and probability is also significant. Large structures amplify errors exponentially. Small errors in individual blocks become measurable discrepancies across massive spans. That the Great Pyramid maintains coherence across 230-meter sides with angular and proportional fidelity demonstrates that the builders imposed constraints that suppressed error propagation at multiple scales. The statistical improbability of achieving such coherence by chance implies that the construction was governed by repeatable, reliable methods, whether through measurement, geometric rules, or both. Taken together, the numerical patterns within the pyramid challenge any explanation based solely on emergent geometry or random coincidence. The perimeter-to-height ratio, corner fidelity, side length consistency, and slope regularity all converge to a single point. The structure embodies mathematical intentionality. Whether this was formalized in abstract units, guided by physical measurement standards, or derived from empirical refinement over multiple iterations, the outcome is statistically extraordinary. Random processes could not produce such multidimensional coherence.
And yet, despite the overwhelming precision, some questions remain. Were these proportions derived consciously, with an understanding of abstract constants and mathematical principles? Or did they emerge as a byproduct of disciplined empirical methods, repeated measurement, correction, and refinement, applied rigorously at every stage? The statistical evidence suggests intention, but the methods remain largely invisible, hidden in the practices, tools, and organization of a civilization more than 4 millennia ago.
The pyramid's geometry forces us to reconsider our assumptions about ancient knowledge. Its proportional coherence is not merely symbolic or aesthetic, it is demonstrably unlikely to arise without deliberate control. When we measure, calculate, and model these dimensions, the numbers tell a story of extraordinary precision, integrated measurement, and systematic control across scale. It is a story that challenges our understanding of probability, scaling, and the capabilities of a civilization without modern instruments or computation. If the Great Pyramid's geometry is intentional, it represents one of the earliest and most complete applications of applied mathematics at monumental scale. Each measurement, each course, each block placement was not only a physical action, but also a numerical act, reinforcing coherence across the entire structure. The statistical improbability underscores the significance of these actions. This is not chance, it is design. The question that remains, and the question that continues to fascinate mathematicians, engineers, and archaeologists alike, is whether this precision was achieved consciously as a testament to mathematical insight, or whether it emerged as a rigorous product of disciplined practice and iterative correction. Either way, the Great Pyramid stands as a monument to the control of geometry across scale, in a way that even modern construction struggles to replicate. If you are intrigued by the mathematical precision and the engineering brilliance of the Great Pyramid, make sure to subscribe and continue exploring the mysteries that blend science, history, and geometry in ways that challenge our understanding of human achievement.
In modern engineering, the prevailing philosophy is one of continuous monitoring and correction. Bridges sway and are damped with tuned mass systems. Skyscrapers are surveyed and realigned if settlement exceeds tolerances, and tunnels are constantly inspected for water infiltration or misalignment. These systems assume that error is inevitable. It will arise, it will propagate, and only through detection and iterative correction can stability be maintained. Feedback loops, both mechanical and procedural, are essential. Sensors detect deviation, computers calculate compensatory adjustments, and human operators implement corrections. Error, in this mindset, is a variable to manage, not eliminate.
The Great Pyramid, by contrast, appears to embody a different approach, one of prevention rather than correction. From the outset, constraints were embedded into the construction process. The bedrock was carved to a precise plane, establishing an invariant baseline. Orientation to true north was determined using gravity and stellar alignment, anchoring the structure in absolute reference frames. The first course of blocks was leveled and squared with extraordinary care, providing a geometric template that successive courses could inherit. By establishing these constraints at the beginning, the builders reduced the potential for error to propagate. The pyramid's stability was not dependent on later correction, it was built into the system itself. Feedback loops in this context operate differently. In modern structures, feedback is reactive. Sensors detect deflection or vibration, triggering corrective action. In the pyramid, the feedback is inherent to the physical relationships between stones and the geometric framework. If a block deviates from the intended plane, the interface itself, the contact with surrounding stones, restricts movement and forces adjustment. Angular deviations are constrained by perpendicular alignments established at the foundation. Linear displacement is limited by standardized units and careful measurement. In essence, the system enforces its own stability through design, rather than requiring active intervention after the fact. Glenn Dash's reconstruction of the pyramid's baselines using linear regression demonstrates the result of this philosophy. By analyzing corner positions, edge alignments, and baseline coordinates, Dash was able to identify patterns of geometric regularity that persisted despite minor, unavoidable variances in individual blocks. Regression analysis allows us to model the intended design across imperfect data points, revealing an underlying system that constrains error propagation. Deviations are small and systematic rather than random, suggesting that each stage of construction inherited stability from the previous one.
This approach contrasts sharply with modern project management techniques. Contemporary construction often relies on layering. Initial stages are completed with tolerance for adjustment, subsequent stages are monitored, and cumulative errors are corrected at intervals. Large structures like tunnels or high-rise towers are segmented precisely because continuous perfection is impossible. Each segment is assumed to have some degree of deviation. Systems engineers then calculate compensatory measures, inserting corrections where necessary. This layering introduces its own complexity. Every correction must account for previous adjustments, and the interaction between layers can create secondary instabilities.
In the pyramid, the philosophy seems reversed. Instead of correcting errors after they occur, the builders appear to have constrained them at the outset. Right angles, leveling, orientation, and unit-based measurements all serve as preventive controls. Micro-precision in casing stones further enforces adherence to the intended geometry. Each block, each course, and each alignment is part of a coherent system designed to propagate stability forward. The construction process itself embodies error management, not as reaction but as prevention. The difference is profound. Modern structures accept that error exists and must be corrected. The pyramid treats error as a variable to be constrained before it arises. Linear propagation of geometry ensures that the intended shape, alignment, and proportion persist across scale. By embedding constraints early, the builders eliminated or minimized classes of error that modern engineers must actively monitor and correct. Nonlinear instabilities, the kind that plague bridges, tunnels, and high-rises, are inherently suppressed because the system is self-enforcing. This philosophy also extends to human organization. Large-scale projects today require extensive coordination, schedules, and monitoring to ensure that each crew adheres to design specifications. In the pyramid, evidence suggests that the measurement system itself, along with ritualized procedures like the stretching of the cord, encoded standards and expectations directly into the construction process. Compliance was less a matter of supervision and more a consequence of the geometric system, the tools, and the established reference framework.
Each worker operated within a system that enforced correctness intrinsically. The contrast highlights a deeper understanding of structural behavior. In contemporary engineering, error detection and correction consume significant resources and time, and residual error is always a factor. The pyramid demonstrates that by anticipating error and constraining it through the design of the system, one can propagate stability over immense scale with minimal active intervention. Linear regression of survey data confirms that deviations are small, consistent and predictable, reflecting a propagation of geometry rather than reactive adjustment. This leads to an intriguing question. Did the builders of the Great Pyramid possess an intuitive grasp of systems engineering principles long before such concepts were formalized? Did they understand, empirically and through practice, that embedding constraints and stabilizing references at the foundation allows errors to be prevented rather than corrected? The structure suggests a philosophy of construction where the system itself governs precision, where geometry enforces compliance, and where stability is a product of design rather than continual adjustment. Whatever the case, the pyramid's enduring precision across millennia stands as evidence that prevention, the careful embedding of constraints and reference standards, can outperform even the most sophisticated corrective systems. Modern engineering may rely on sensors, computers, and iterative adjustments to maintain alignment and stability, yet the pyramid achieves equivalent or superior results through careful planning, measurement, and the propagation of geometric discipline. The approach is elegant, efficient, and profoundly effective, demonstrating that constraint-based prevention can rival reactive correction in controlling complexity over vast scale. If you find the idea of preventing errors through design rather than correcting them fascinating, make sure to subscribe and continue exploring the principles that allowed the Great Pyramid to endure with such extraordinary precision. The Great Pyramid did not rise overnight. Its construction, according to archaeological consensus, spanned roughly 2 decades, a period remarkable both for its duration and for the consistency of output it achieved. 20 years of incremental, deliberate work is not merely a reflection of labor availability or political will. It represents a strategy for controlling scale, precision, and error over vast dimensions. When a structure grows slowly, the forces that threaten geometric coherence, misalignment, settlement, cumulative angular deviation can be monitored, managed, and inherently constrained. Rapid construction, by contrast, often amplifies the potential for deviation. Modern engineering projects that attempt to compress schedules frequently encounter just this problem. Accelerated timelines reduce the ability to correct micro-errors before they cascade into macro-scale misalignment. The pyramid's construction methodology reflects this principle. The process involved sequential layering, with each course of stone meticulously placed, leveled and squared before the next layer was added. Archaeological evidence indicates that work was organized into highly coordinated crews, often termed gangs or teams, each responsible for specific segments of the structure. By dividing labor into specialized groups and scheduling their activity across extended periods, the builders ensured that every stone placement was guided not only by human skill, but by an underlying geometric framework. Errors at the block level could be detected and prevented from propagating because the system itself incorporated sufficient temporal margin for correction, review, and adjustment. Documents such as the Mera logbooks provide an extraordinary glimpse into this organizational structure. These papyri, recently discovered and studied, record the transport of limestone from quarries at Tura to Giza, the allocation of crews, and the sequencing of delivery. The logbooks reveal a complex, highly disciplined supply chain that ensured a steady flow of materials, enabling slow, controlled construction rather than rapid, haphazard stacking. The evidence shows a coordination of hundreds of workers, with schedules detailed down to the day and week. Such precise logistics were essential. Even slight interruptions or irregularities in supply could disrupt the delicate balance of geometry, leveling, and alignment. time itself became a stabilizing factor, embedded into the rhythm of labor and material movement. The deliberate pace of construction also mitigated the risk of human error accumulation. Modern projects frequently compress schedules, compelling crews to work in parallel under tight deadlines. In skyscrapers, for example, simultaneous work on multiple floors requires constant coordination to maintain alignment and tolerances. Miscommunication or uneven execution can propagate errors, requiring reactive correction. In contrast, the pyramid's sequential methodology, layer by layer, course by course, effectively decoupled stages of construction, allowing each increment to settle and align before the next was imposed. Errors were constrained spatially and temporally, preventing cumulative deviation from undermining the overall geometry. The slow layering process also interacts with material properties in a stabilizing manner. Limestone, although durable, is not immune to microfractures or settling under its own weight. By placing stones incrementally and allowing minor adjustments, the builders could ensure that each block seated correctly on its predecessors. The weight of successive layers could be distributed evenly because each underlying course had been carefully leveled and compacted. Rapid high-volume placement might have introduced uneven stress, increasing the potential for localized settlement or micro-shifting, which could propagate upward and distort angles. Patience in construction thus functioned as a physical control mechanism, allowing the geometry to propagate without distortion. Temporal control also extended to the calibration of measurement systems. Tools such as the royal Cubit rods, cords for alignment, and sighting instruments could be employed systematically, with crews taking the time to verify right angles, leveling, and orientation at each stage. Each measurement became a point of reference for subsequent work. By spacing activity over months and years, the builders ensured that these reference points remained stable and could be cross-checked against new measurements. The incremental approach reduced the probability of errors compounding across the structure, which is a central challenge in scaling. The integration of workforce management and time as a stabilizing factor is further illustrated by the distribution of labor intensity across seasons. Some evidence suggests that large crews may have been concentrated during periods when the Nile's flood cycle freed additional manpower from agricultural duties. This cyclical scheduling, embedded within the broader 20-year timeline, would have allowed the builders to maintain precision without overloading any single phase of construction. By balancing labor intensity with construction pace, the project could absorb variability in skill, environmental conditions, and material transport without compromising geometric fidelity. In modern construction, compressed schedules often introduce a cascade of issues precisely because time is treated as a constraint to be minimized rather than a variable to manage. Accelerated timelines increase reliance on temporary shoring, rapid material curing, and parallel tasking. Each of these introduces potential error sources that can compound across scale. By contrast, the pyramid's extended timeline acted as a natural error buffer. Minor misalignments or material deviations could be detected and accommodated before they affected the larger structure. The temporal factor was therefore not incidental, it was integral to geometric control. Furthermore, the pace of construction reinforced procedural discipline. Rituals and standardizations, from the stretching of the cord to unit-based measurement practices, were more effective when work proceeded deliberately. Crews could adhere consistently to protocols, double-check alignments, and verify block placement. Deviations were not ignored but actively constrained by both human oversight and physical measurement systems, with time allowing iterative verification. This interaction of labor, tools, and schedule created a self-reinforcing loop. Slower construction enabled higher precision, which reduced the need for reactive correction, which in turn allowed steady progress without geometric compromise. The pyramid's temporal strategy also amplified its integration with the Earth itself. Carving the base into the plateau, leveling courses and establishing precise alignment required observation, assessment, and adjustment. The extended construction period allowed the builders to respond to subtle variations in bedrock or environmental conditions. By distributing work over decades, they avoided the pitfalls of rapid imposition on an imperfect substrate. The earth, the geometry, and the workforce were synchronized through time, creating a system in which incremental progress propagated stability rather than error. Taken together, these observations suggest that time was more than a scheduling consideration. It functioned as an active stabilizer, a built-in control mechanism for scale. 20 years of deliberate incremental construction allowed the builders to manage material behavior, labor variability, environmental factors, and measurement precision simultaneously. Patience replaced reactive correction. Slow layering became a geometric safeguard, enabling the pyramid to maintain angular fidelity, proportional coherence, and alignment over an immense footprint. This raises a fundamental question. Was the extended construction timeline merely a consequence of resource management and logistical reality, or did the Egyptians recognize, implicitly or explicitly, that time itself could stabilize their design? Did they understand, in practical terms, that gradual deliberate layering was essential to maintaining scale invariance and controlling error propagation? The evidence from workforce organization, incremental placement, and meticulous logistics suggests that time was harnessed not just to coordinate labor, but to preserve geometric coherence across the pyramid's massive scale. If you are captivated by how time, patience, and disciplined sequencing contributed to the enduring stability of the Great Pyramid, make sure to subscribe to continue exploring how ancient design principles mastered scale, geometry, and human organization in ways that still challenge modern engineering. After examining the extraordinary coherence of the Great Pyramid, it becomes impossible to ignore the contrast with later pyramid constructions. Within a single generation, the precision that marked Khufu's monumental achievement begins to erode. Measurements taken from the Pyramid of Khafra and the Red Pyramid demonstrate increasing deviation from ideal baselines. Corner angles drift from near-perfect right angles by several minutes of arc, side lengths vary more noticeably, and cardinal orientation loses the almost obsessive fidelity found in Khufu's structure. Even the later Pyramid of Menkaure shows compounded discrepancies. Whereas Khufu's pyramid had corners accurate to approximately 45 arc seconds and sides within 20 centimeters, Menkaure's corners deviate by more than a minute of arc, and side length differences are measurable across multiple meters. Several factors contributed to this decline, both technical and social. Khufu's reign coincided with a period of centralized authority, unprecedented resource allocation, and meticulous administrative oversight. Archaeological evidence suggests that quarrying, transportation, and workforce management were tightly coordinated. The Mira logbooks illustrate a level of bureaucratic precision that ensured steady supply lines, coordinated labor gangs, and a rhythm of work aligned with both the Nile's seasonal cycle and ceremonial observances. Later pharaohs, facing internal and external pressures, could not always maintain such exacting oversight. Centralized control diminished, and resource constraints grew more acute. The level of logistical coordination that had enabled Khufu's geometric discipline was not fully replicated in subsequent projects. This decline is visible not only in structural measurements, but in the treatment of materials. The Red Pyramid at Dahshur, constructed under Sneferu, exhibits some of the largest deviations in slope uniformity across the faces. Even though the underlying metrological and measurement tools were presumably available, the execution was less rigorous. Coarser stone, less meticulous finishing, and uneven placement contributed to cumulative error. The smaller and steeper pyramids of the 5th dynasty show even more pronounced deviations. The effect is not gradual. It is abrupt enough to suggest that precision was actively maintained under Khufu and deliberately relaxed in later periods. Methodological rigor seems to have eroded over time. The precise application of Cubit rods, the systematic stretching of chords, and the repeated verification of perpendiculars, all evident in Khufu's project, become harder to detect in later pyramids. The alignment of the Red Pyramid is still remarkable, but fails to achieve the same statistical improbability as the Great Pyramid. The perimeter-to-height ratios diverge further from idealized values, corner angles drift more, and the base is less perfectly level. Scholars such as Mark Lehner have observed that even minor increases in error at the base propagate through the structure, compounding in ways that are easy to detect millennia later. These deviations illustrate that precision was not an inevitable property of Egyptian pyramid construction. It required active, disciplined application. Social and political contexts likely influenced the decline as much as technical factors. The immense labor and resources required to achieve Khufu's level of precision could only be sustained under a regime with centralized authority and abundant resources. Subsequent pharaohs faced changing priorities, economic pressures, and shifts in religious focus. Sneferu's Red Pyramid and Bent Pyramid show ambitious experimentation with shape and angle, suggesting that innovation sometimes competed with exacting geometric fidelity. The introduction of steeper angles or internal corbelling may have compounded technical challenges, making the precise application of base-level geometry more difficult. The decline in precision also illustrates the limits of material and workforce control. Khufu's teams worked with consistent limestone quality from Tura and carefully carved local blocks for the core. Later projects often relied on less uniform materials or on crews operating with less direct supervision. The systematic measurement of units, which allowed error propagation to be minimized under Khufu, may have been relaxed or inconsistently applied. Microscale precision, such as the 0.5 mm joint tolerances documented in the original casing stones, was no longer consistently achieved. Minor variances at the block level, when multiplied across hundreds of courses, produced measurable deviations at the macro scale. Even the ceremonial aspects may have changed. The stretching of the chord ritual, once used to define perpendiculars and alignments with astronomical reference points, may have been altered or abbreviated. The reliance on observational astronomy for cardinal orientation may have diminished, leading to incremental misalignment. The fact that deviations appear in both angular and linear dimensions across successive pyramids suggests that procedural discipline rather than inherent technological limitation was the critical factor. Examples of decline are telling. At the Red Pyramid, the northeast corner deviates several centimeters from its projected position relative to the other corners. The slope of the northern face differs slightly from the southern, producing a subtle asymmetry. At the Menkaure Pyramid, the southwest corner drifts more than 50 centimeters, and angular discrepancies exceed a minute of arc. These differences, though minor on a human scale, are orders of magnitude greater than the tolerances achieved at Khufu's pyramid. They reflect not a limitation of materials or tools, but a relaxation in organizational discipline, measurement verification, and foundational rigor. The contrast underscores a central insight. The extraordinary precision of the Great Pyramid was the product of deliberate, repeatable methods applied with extraordinary care. It was not accidental. Khufu's reign appears to represent a peak in applied measurement science, an era in which geometric control, workforce management, metrology, and foundation engineering coalesced to produce unprecedented coherence. Later pyramids demonstrate that precision can easily decline without continuous adherence to these principles. The implications extend beyond ancient Egypt. They reveal that even societies with sophisticated tools and knowledge cannot guarantee geometric fidelity without systemic discipline. High precision is contingent, not automatic. Environmental conditions, resource allocation, and organizational rigor all determine whether scale can be maintained. The Great Pyramid, in this light, is more than a monument. It is a testament to human capacity for coordinated measurement and applied engineering at a scale rarely matched before or since. Khufu's pyramid remains a singular achievement, standing at the apex of a brief but extraordinary period in which geometry, physics, and organizational discipline aligned perfectly. The decline in precision in subsequent pyramids serves as evidence that the feats of Giza were neither inevitable nor accidental. They required intentionality, planning, and an unrelenting commitment to measurement. The lessons embedded in this decline are as instructive as the pyramid itself. Precision requires effort, and even the most advanced techniques will falter if rigor is relaxed. By examining these contrasts, it becomes clear that Khufu's reign was not merely a historical epoch. It was a high watermark for applied measurement science. It demonstrates that the extraordinary fidelity of the Great Pyramid was not the product of chance, but the result of a society capable of aligning human labor, material science, and geometric principles with extraordinary discipline, creating a structure that would endure with near-perfect coherence for millennia. Scale invariance is a concept that stretches far beyond the quarries of ancient Egypt, extending into the deepest reaches of physics, mathematics, and cosmology. At its core, it describes systems in which certain properties remain consistent regardless of scale. In fractal geometry, a structure exhibits self-similarity, zoom in or out, and the pattern repeats, maintaining its essential character. In cosmology, certain physical laws, from the distribution of galaxies to the turbulent eddies of interstellar gas, reveal patterns that are remarkably consistent across vast ranges of scale. Scale invariance is a signature of underlying order, a principle that resists degradation as systems grow or shrink. The Great Pyramid exemplifies this principle in a physical, measurable way. From the millimeter tolerances between casing stones to the hundreds of meters spanning its base, the pyramid maintains proportional fidelity. The angles, slopes, and linear dimensions cohere not only in isolated segments, but across the structure as a whole. Minor deviations at the microscale, a fraction of a millimeter in a stone joint, do not amplify into catastrophic errors across the macro-scale footprint. The system behaves as if the geometric laws it embodies propagate consistently, unperturbed by the challenges that usually accompany massive structures. By contrast, most human constructions today experience what physicists and engineers call nonlinear scaling failure. As structures increase in size, stress, displacement, thermal expansion, and cumulative tolerances no longer scale linearly. Bridges sway more than predicted, skyscrapers settle unevenly, and tunnels misalign under their own weight. Material strength laws impose limits, and deviations at one scale multiply unpredictably when projected to a larger system. The pyramid, however, avoids these pitfalls. Its integration with bedrock, its careful layering, and its embedded measurement constraints allow forces and geometric relationships to propagate without triggering nonlinear instabilities. Scale invariance is preserved not by luck, but by design. This phenomenon introduces a philosophical dimension. Geometry, in this sense, becomes more than a tool for construction. It becomes a medium of intelligence. A structure that maintains proportional fidelity across scales demonstrates foresight, control, and an understanding of constraints that is fundamentally abstract. The Great Pyramid does not merely occupy physical space, it encodes a geometric system that resists error propagation, a system in which the relationship between parts and whole is consistent and coherent. This is the hallmark of intelligence applied to matter, the ability to foresee consequences across scales and to embed rules that preserve order against natural forces of deviation. One can imagine the pyramid as a physical manifestation of scale invariance, an invariant system in which geometry itself governs stability. Each stone, each course, and each angular alignment reinforces the integrity of the whole, much like repeated fractal iterations reinforce the overall pattern. The concept extends beyond measurement into the philosophical. To create something that maintains coherence across scale is to impose a kind of abstract order upon a world that is inherently subject to entropy and randomness. Yet scale invariance is not absolute. In physics, systems eventually encounter thresholds, limits imposed by material strength, thermal expansion, or chaotic interactions. The pyramid skirts these thresholds through meticulous attention to mass distribution, angular fidelity, and foundational stability. It demonstrates that careful design, guided by principle rather than trial, can maintain coherence in a system even when the scale is massive. This invites a provocative question. When a system preserves its integrity across scale, is that an expression of intelligence in its design? In the case of the Great Pyramid, the evidence points toward deliberate control. The builders created a structure that maintained proportional fidelity from the smallest measurement of a casing joint to the monumental scale of the entire edifice. The principle of scale invariance, observed in natural and mathematical systems, is mirrored in human action, and in doing so becomes a subtle testament to the capacity for foresight, abstraction, and the management of complexity. The pyramid challenges us to consider intelligence not as raw computational power or mechanized correction, but as the ability to conceive a system whose behavior is consistent, predictable, and coherent across vast differences in scale. It is a philosophy embedded in stone. That order, when properly understood and applied, can resist the compounding effects of size, weight, and time. Here, physics, mathematics, and philosophy converge, leaving a structure that is simultaneously monumental and conceptually elegant, a tangible proof that scale invariance is not only a property of natural law, but also a possible signature of human insight. The Great Pyramid is not only a monument of stone, it is the culmination of a civilization operating as a measurement machine. Over 2,300,000 limestone blocks were quarried, transported, cut, and placed with astonishing precision. Each block had to fit within a structure whose sides measured over 200 meters, whose corners deviated by mere seconds of arc, and whose base was level within centimeters. Achieving this required coordination on a scale that would challenge any modern enterprise. Every aspect of labor, from quarrying to placement, was linked through carefully maintained schedules, standardized procedures, and hierarchical oversight. The rhythm of work across decades ensured that the precision of one generation of laborers was inherited by the next, without the need for written instructions or detailed engineering manuals. The flow of resources was equally critical. Limestone from Tura was floated down the Nile, granite from Aswan transported hundreds of kilometers, copper tools maintained and replaced, and food, water, and shelter supplied to thousands of workers. Papyrus records, most notably the Mera logbooks, document this logistical ballet, showing that material transport and workforce allocation were planned with the same rigor as the construction itself. Coordinating thousands of individuals, each contributing to a geometric whole, required institutional memory. Rituals, measurement standards, and verification processes preserved knowledge across shifts, seasons, and even decades. In modern industrial terms, one might compare this to ISO standards or quality management systems. ISO ensures that procedures, tolerances, and outputs meet consistent criteria regardless of who performs the work. In the absence of written codes, the Egyptians relied on ritualized procedures, physical measurement tools, and repeated verification. The stretching of the chord ceremonies, cubit rods, and alignment markers functioned as embedded quality control mechanisms. Process control was built into the society itself. Workers were part of a system that propagated geometric precision as a function of labor, material, and measurement acting in concert. Every layer of the pyramid, every stone placement, was the product of this integrated system. Deviations were constrained by prior alignment, by standardized measurement units, and by social and procedural discipline. The pyramid's stability was not a property of individual skill alone, but emerged from the collective application of measurement across an entire civilization. The combination of human organization, institutional memory, and environmental understanding created a system capable of achieving coherence that modern projects struggle to replicate, even with digital tools, automated machinery, and written engineering codes. This perspective reframes the pyramid as more than architecture. It is a record of coordination, a monument not only to geometry but to the capacity of society itself to function as a single instrument of measurement and control. Labor, materials, and process were synchronized over decades to produce a structure whose precision transcends individual effort. The civilization acted as a living metrology machine, encoding knowledge, enforcing standards, and maintaining alignment across time. And yet a profound question remains. Why channel such immense social, technical, and temporal resources into absolute precision? Was it purely symbolic, a demonstration of authority, or was there an understanding that accuracy itself carried a deeper purpose, perhaps in astronomy, mathematics, or the alignment of human activity with cosmic reference points? The answer is obscured by time, but the evidence of systemic control speaks clearly. This civilization measured not just stone, but itself, aligning its collective effort to create a monument that has endured with an intelligence encoded in its very proportions. Our ancestors were way more civilized and intelligent than us. Do you agree with it? Across millennia, the Great Pyramid stands not merely as a testament to human ambition, but as a demonstration of what happens when scale, precision, and time are harmonized. Modern megaprojects, from cantilevered bridges to towering skyscrapers, often falter under the weight of their own complexity. Settlements, oscillations, thermal stresses, misalignments. These are the inevitable consequences when scaling outstrips control. Yet the pyramid defies that pattern. It is not the height or the mass that impresses, it is the coherence that persists across dimensions. The way geometry propagates from the millimeter joint to the 230-meter base without faltering. Here, the pyramid becomes more than stone. It becomes a reference frame, a physical embodiment of invariant baselines. Every alignment, every right angle, every leveling plane anchors the structure to immutable principles: gravity, cardinal directions, proportionality. The civilization that built it functioned as a single, distributed instrument, transmitting these standards across decades, generations, and millions of blocks. Constraint, discipline, and careful measurement were far more powerful than brute force or sheer size. Complexity alone did not achieve stability, precision did. Geometry mattered more than mass. Scale, when anchored to invariant references, need not break the system. This insight carries a philosophical resonance. Civilizations, technologies, even our daily lives depend on reference points. Our social, scientific, and moral frameworks function as baselines. Yet, in an age of accelerating change, what are our modern baselines? When networks fail, economies fluctuate, and measurements lose coherence, the fragility of contemporary systems becomes apparent. The pyramid reminds us that stability arises not from raw power or abundance, but from the careful establishment of immutable references, from embedding constraints that prevent error before it accumulates. In the end, the lesson is stark and existential. Empires crumble, materials erode, instruments fail, but invariant baselines endure. When our own reference frames collapse, when conventions, technologies, and beliefs are shaken to their foundations, what remains? What is truly immutable in a world in motion? The Great Pyramid offers a silent answer. The geometry, the principles, and the standards that bind a system from its foundation upward can survive when everything else falls away. It is not merely a monument to the past, it is a challenge to the present, a question to every society. What will remain invariant when our own scales and baselines are tested? Thank you for joining us on this extraordinary journey through the universe on Frontiers of Infinity. If this glimpse into the unknown has sparked your curiosity, be sure to subscribe and join us, where we unravel the darkest mysteries of space.